Hi class, we're just going to go over some easy little results that will allow us to do more complicated things a little bit later on. So some nifty properties. Here's our first theorem, namely that the probability of the complement event equals 1 minus the probability of the original event. That kind of makes sense. It's kind of the opposite of the original event. Here's a proof. I'm just going to show you this just to see what these kinds of things look like. I mean, I suppose you could do a elementary little Venn diagram argument, but let's do the formal math proof. By axiom 2, something's got to happen from the sample space. So that means that 1 equals the probability of something occurring in the sample space. Now, the sample space is just A union A bar. Either A happens or it doesn't happen. Something's got to happen. Because A and A bar, the complement event, are disjoint by definition, we know that the probability of the union is the sum of the probabilities, at least when A and A bar are disjoint, which they are. That's just axiom 3. So see the little box at the end of the line? That means we're done. The proof is over because 1 equals P of A plus P of A bar. That's just what the theorem says, except we have P of A bar on the left-hand side. But that's it. As an example, well, let's pretend that A is the event that it won't rain tomorrow. So that means the probability that it will rain tomorrow is 1 minus the probability that it won't rain. So real easy, right? Now let's look at a corollary of that first theorem. Namely, the probability of the null set equals 0. And what that means is you can't observe no outcome. Probability 0 of observing no outcome from the sample space. Or that's equivalent to you must observe some outcome from the sample space. The proof is really easy here. By definition, the null set equals the opposite of the sample space, S bar. So the result follows from that first theorem and axiom 2. Because we know that the probability of the sample space is 1, the opposite of that, 1 minus 1, is 0. Done, done, done. Here's an extremely cool remark. Namely, the converse of the corollary is false. So what this means, the regular corollary just says the probability of the null set is 0, but if something has probability 0, it doesn't mean that it's the null set. So P of A equals 0 does not imply that A is the null set. And here's sort of the bellwether example for that. Let's pick a random number between 0 and 1. There's a lot of numbers between 0 and 1. In fact, an uncountable number. So each particular number that you could pick has probability 0. So let's suppose I pick 0.507321. Well, even though I picked it, it has probability 0 of being picked. I know that's a little crazy sounding, but any individual number has probability 0. But I picked a number. It's not the null set. So I picked something that has probability 0, but it's not the null set. It was a number. Okay, so all I'm going to do, I just want you to think about that for a while, and we'll talk about that in gross and tedious detail later on. Here's our next theorem. For any two events A and B, the probability of the union is the sum of the probabilities, what's this? Minus the probability of A intersect B. So the probability of A union B is P of A plus P of B minus P of A intersect B. Now, you may be thinking, well, why do I have that intersect probability there? Because this theorem is more general than that old axiom. Here, the two events don't have to be disjoint. In our axiom, they had to be disjoint. So here they don't have to be, and by subtracting off the intersection, that takes into account the fact that they might not be disjoint. So here's a proof. I'm going to use an easy Venn diagram argument here. I mean, it's not really mathematically rigorous, but it's good enough. And let's take a look at the picture. I've got in red A, in blue B, and so if I add up A and B, it looks like I've double counted that middle portion in yellow, A intersect B. I've double counted it. So that means I just subtract it off. Bang, I'm done with the proof. And like I said, axiom 3 is a special case of this theorem in the very special case that A and B happen to equal the null set if there's no intersection. Let's do a simple little example illustrating this theorem. Let's suppose there's a 40% chance of colder weather tomorrow, 10% chance of rain and intersect colder weather, and 80% chance of rain or union colder weather. Okay, so P of C equals 0.4, P of R and C equals 0.1, probability of rain R or C, colder weather, is 0.8. So we'll see what this means in math terms in a second. So let's find the chance of rain, and just manipulating the equation from the theorem, you'll see now that the probability of rain or cold, this is substituting for A or B on the previous theorem. That probability is on the right-hand side, and I've just scrambled things around a little bit, but it's coming from the same equation. So the probability of rain, R, equals the probability of rain or cold minus the probability of cold plus the intersection. Substituting in, the probability of rain or cold is 0.8, minus the probability of cold is 0.4, plus the probability of the intersection is 0.1, and I get 0.5 in all. Just a plug and chug, very easy. Now I'm going to generalize that theorem. Now I'm going to look at three events, A, B, and C, because 2 is wussy. So the probability of A or B or C equals the following mess. P of A plus P of B plus C of B minus all the possible intersections of two things plus all the intersections, there's just one of them, of three things. So this is very interesting. I add up all the single probabilities, subtract off all the double probabilities, and add up, there's only one, the triple probability. I'm not going to formally prove this here. I mean, if you want to prove it, go ahead. It's possible. It's slightly easier if you use Venn diagrams, but you've got to be very, very careful about double and triple counting things. That's why you have the minus signs and the events. I would ask you for now, just take my word for this guy. It's true, so take my word for it. And it's looking a little daunting maybe, but it's actually a pretty easy equation. Here's an example. Suppose that 70% of Atlantans jog, we'll call that J, 20% like ice cream, I, and 40% enjoy music, M. Also suppose that 15% like jogging and ice cream, J intersect I, 30% jogging and music, 10% like ice cream and music, so that's the intersection of I and M, and 5% like all three activities. Let's find the probability that a random guy from Atlanta, a random person from Atlanta, engages in at least one of the three activities. So that's just written as the probability of J or I or M. I'm going to plug into the mess from the last page, add up all the individual guys, subtract off all the intersections of two things, and add on the intersection of three things. It is so easy. P of J, 0.75, P of I, 0.2, blah, 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 blah. Eventually we get down to the probability of the triple intersection, which is 0.05. Add and subtract them all up, and I can say that the probability that we do jogging or ice cream or music or any combination thereof is 0.85. Pretty easy. Let's do a slightly more difficult problem. Namely, let's find the probability of engaging in precisely one activity. Not two, not three, not zero, but exactly one. So here's the situation from the last page. What I'm going to do, it's very, very interesting. I'm going to start with everything from the last page, in particular that last piece of information that the probability of the triple intersection is 0.05. I'm going to start from the center, and just like the movie Aliens, I'm going to eat my way out. So here we go. This is the picture. You can see in the middle, I have that probability 0.05. That's the probability of J intersect I intersect M. Now, I'm also going to remember that the probability of J intersect I, so jogging and ice cream, is 15%. See, look at that. There's 15%. I've already taken into account the 5% from the triple intersection. So this area right here, which is J intersect I but not intersect M, so that's 0.10. And these two things added together, 0.15. Similarly, the probability of J intersect M, as in music, is 30%. The probability of I intersect M is 10%. So you can see how all this stuff is working out. And in particular, let's look at this. The probability of J, you just add up all these things, and you get, let's see, what is it? 0.35 plus 0.25 plus 0.05 plus 0.1. That looks like, if I can above my head, 0.75. So that's very easy, and that adheres to what we saw on the last page. So now, what do I want in this problem? I want this piece here, only jogging. I want this piece here, only ice cream. And this piece here, only music. And you can see that the answer should be 0.40. Let's look at this now in math terms. Probability of only jogging, only ice cream, only music. And in terms of those nasty looking intersections, you can see the first term is J and not I and not M, etc., etc. I plug in, I get 0.35, 0, 0.05, and that adds up to 0.4, just like you could see from the picture. A little bit more work than the last example, but not bad at all. Okay, now we're experts on this stuff, adding up the probabilities, subtracting intersections, adding the intersections, and here's the most general result. This theorem is called the principle of inclusion-exclusion, and this gigantic, horrible mess is the probability of the union of an arbitrary number of events. And you can see, I'm not going to go into the details. What we find is that we add up all the individual probabilities, we subtract off all the double probabilities, we add the triple probabilities ad infinitum. And it just goes on and on. It's a big mess, but a nice result. We will actually use this a couple times. What this is saying is that you include all the single guys, exclude the double guys, include the triple guys, etc., etc. The proof of this is tedious, and totally you don't need to do it, but the previous two theorems are very nice special cases. Okay, very good. We got through this lesson. In the next lesson, we'll be talking about finite sample spaces. So we'll see you then.